Welcome to this circuit protection presentation by Diodes Incorporated. My name is Isaac Sibson and I'm the Automotive Applications Engineer for Europe and North America. As we go through this presentation, we'll cover a number of topics, starting with what is protection, what are we protecting, against what and how. We'll talk about some of the devices and some of the circuit configurations we might use to do this, and we'll talk about some other system level considerations. What do we mean by protection in the context of an electronic circuit? We could start with this as a definition. Keep the circuit safe and functional in the face of external threats. What sort of external threats? Well, what about this? What about this? What about this? Of course, we can't protect against everything. So we let us make the circuit survive foreseeable and reasonable threats. In the cases above of running over a phone with a car or dropping it down the toilet, obviously that's a problem for the mechanical engineers. We're dealing with the electronics, so what are we going to talk about? So we're going to talk about electronic threats. What sorts of threats might these be? We'll start off with a simple spike, and I think the most obvious and most damaging example of that would be ESD discharges. We might also talk about a surge, such as a lightning strike on a telecom system, that although lower magnitude than an ESD spike, does have longer duration and more energy. We might consider an overvoltage situation or an overcurrent situation as a significant threat, and indeed a reverse polarity situation. And I think, hopefully, you can see that these would fall into two camps. We'd split it down the middle, that on the right we have the steady state threats, and on the left we have the transient threats. How might we protect against some of these threats then? To begin with, we can start with some passive components such as inductors, capacitors, and even resistors, and use these to build up filter networks. We can start to use active components such as the TVS, the Transient Voltage Suppressor, and we can build up circuits for overvoltage, overcurrent protection schemes and switch in and out relays. Like the previous slide, we can split these down the middle and consider that the passive and TVS components will work for transient threats, and that circuit detection and mitigation schemes are more suited to steady-state threats. A key thing to bear in mind with protection is that we need it to do something. We wouldn't put it in if we didn't need it to do something. But we want it to do nothing. And by this I have two particular meanings. One is that it would be lovely if we put a TVS in a circuit and we never actually have an ESD discharge situation that requires it to do anything. But the other is that protection is not the primary goal of any circuit. It's an ancillary function that just means that circuit will continue to exist for a longer time. And the protection scheme must not adversely impact the operation of the circuit's primary function, whether it's high-speed data, some sort of sensor, power supply, whatever it may be. It's useful to consider the concept of protection margins. Any circuit that we design will have a normal operating area, a maximum input or output voltage, and maximum input or output current. Engineers, being engineers, we will always give ourselves some leeway. If our circuit has a maximum operating voltage of 5 volts, we're going to have components that will tolerate 7 to 10 volts as a minimum in that circuit. Above that level, there will be voltage damage caused to the components. And similarly for current, there will be some leeway. It is this blue shaded area that represents that leeway that we can consider as the place where we want our protection to work. If we can make the protection operate within these margins, we know that the circuit won't be damaged. So to begin with, let's have a look at the TVS, the Transient Voltage Suppressor. Now here the clue really is in the name as to what this does. It suppresses voltage transients. It's a Zener device, and we'll understand some of the characteristics that you might see in the datasheet. Let's talk about power handling, the difference between unidirectional and bidirectional devices, the capacitance, and some of the ways that the devices are packaged together. To begin with, though, how do we implement a TVS? And it's really quite simple. You have two voltage rails or two voltage points, and you just simply put the device across the two. It will clamp any transient above a given level between these 2 points. So let's have a look at the characteristics of the TVS. The IV characteristic is akin to any other Zener device, that once a certain voltage level is reached, then there's a breakpoint in the characteristic, at which point the current conducted will increase rapidly. There's a number of parameters on the datasheet, and it's important to understand how they fall into the IV characteristic. So to begin with, VRWM, the reverse working voltage. This is the headline figure for a TVS device. This is the voltage that you see in the part number or as the first figure on the datasheet. And what this actually means is that this is the voltage at which the device is guaranteed not to leak more than a certain amount of current. And it will be specified in the datasheet what that current is. It might be 100 microamps, it might be 10, it might be 1 microamp, but a small figure. The next point to be aware of is the actual breakdown voltage. And again, the datasheet definition of this will be at a given current to begin conduction, so for example 10 milliamps, what is the voltage range that you would measure of the devices? The next characteristic that becomes very important is the peak power limit, and this is dictated solely by the die size of the TVS device. And from that, two other parameters are derived. The first being the clamping voltage, and the next being the peak current. If we now bring in our protection margins from the previous slide, you can see how we want to align some of these characteristics to the margin that we might have. It's important to note that you can put in a 5-volt TVS onto a 5-volt rail. You understand that the 5 volts reverse working voltage means that you have a maximum leakage that you'll be dealing with. So if we have a look at a real datasheet example, and this data table taken from the Diodes Incorporated DFLT series datasheet, you can see that the DFLT 5V0 part here has, as we discussed, a reverse working voltage of 5 volts. And in this column over here, we can see that that means at 5 volts, this device is guaranteed to leak no more than 400 microamps. You can see as the working voltage of these devices increases, the leakage currents decrease. Then when we have a look here at the breakdown voltage column, you'll see the notation VBR at IT, with IT stated in this column here. So that means that when this device passes 10 milliamps of current, it will be doing so with a voltage of 6.4 to 7 volts across it. Notice that the tolerance lines up such that a low breakdown voltage DFLT 6V0 might have a lower voltage than a high voltage DFLT 5V0. And finally, in the right hand two columns, we see the maximum current and voltage given for each device. And within a series like the DFLT series, where there is a peak power rating of 225 watts given, you'll find that the product of these two columns for all parts here is the same. It's the 225 watts peak power. Let's talk about power handling. If we start with a fairly common, well-known device that many of you will have come across, a 3.0 SMCJ20A. And if we read the datasheet, the headline of the datasheet describes it as a 3000 watt surface mount transient voltage suppressor. Now, hang on a minute. Read that again. 3000 watt surface mount. Ordinarily, these are not words we would put together in a sentence without another word like fire. So what are we actually talking about here? And I would hope it's obvious that the answer is time. Time is the key factor here. that a peak power dissipation of 3000 watts for a very short time gives you a certain amount of energy, and these figures are to give you a guide as to how much energy the device can handle. There are two standards for this that are widely used, the shorter 820 microsecond pulse and the 10-1000 microsecond pulse. It's important to note that the times given here are elapsed time from zero, so the 820 pulse spends 8 microseconds climbing up to its peak, and then a further 12 microseconds declining to 50% of its peak value. The 10-1000 pulse similarly spends 10 microseconds going up and 990 microseconds coming down, although the difference between 990 and 1000 in that case is obviously trivial. These very short-term power ratings obviously reflect a much more accurate real-world use case for the TVS. The TVS is not a steady-state device, it's a transient device. You need to think of these pulses as showing the shaded areas under the curve as the energy that will be dissipated in the device. So as we continue to look at power handling, what we'll see is that when you are looking at the 820 pulse, both the VCL and the IPP numbers will be higher than for the 10-1000 pulse, and so as such the product of the current and voltage will give a much higher power rating for the shorter pulse. If we relate that back again to a real-world datasheet, and again I'm using the Diodes Inc. DFLT series, what we'll see is that the 820 power handling is actually 5 times as high as the 10-1000. You can also see that there is a given steady-state power dissipation figure, but as I've already said, this is largely meaningless in the case of a TVS. Something important to consider is that for a TVS, because of these very short-term pulses, PCB area and heat sinking are irrelevant. This is about the actual die of the device heating up and taking that energy. If the die is starting at an elevated temperature, it will have less remaining capacity to absorb further energy. An often misunderstood aspect of TVS devices is that of directionality. The standard basic TVS device is referred to as unidirectional. We've discussed the IV characteristic of this device in the top right quadrant, but what happens if you apply voltage in the other direction? As was in a device, there's simply a VF, and after which the current conducted increases rapidly, which is to say that a unidirectional TVS would clamp a negative going spike very quickly. A bidirectional device is most easily thought of as two unidirectional devices opposed. If we do that, then I think you can see that your voltage characteristic would be shifted to the right by the VF, and it would be the same in the opposite direction. This gives you the bidirectional device, which allows you to then have an operating area in the bottom left quadrant, such as in the case of a split rail audio system where there are negative going voltages. The total breakdown voltage in any direction is the forward breakdown voltage of the one device plus the reverse breakdown voltage of the other. They don't necessarily have to be the same. There are cases where there are asymmetric bidirectional TVSs. A common case would be a LIN bus device for automotive. We already discussed the idea that we want our protection to have minimal possible impact on the circuit that we're protecting, and the capacitance of the TVS device can be a significant factor in that, particularly when we're dealing with high-speed data. Capacitance is inherent to the PN junction of the Zener device. It's higher in low breakdown voltage parts because the depletion region is narrower, and the root cause of the capacitance is charge carriers either side of a depletion region. This sounds like the construction of a capacitor. Putting two capacitances in series in a bidirectional part means that the capacitance is thus lower. Larger devices with a higher power handling capability will have a higher capacitance because of the larger die area. As we've said, that would be a problem for high-speed data, but one possible solution to that is to use a low capacitance rectifying diode. If we start with our basic TVS that might have a capacitance of 1 nanofarad, if we put the rectifying diode in series with it with a capacitance of 1 picofarad, you can see that that would drastically reduce the capacitance. However, we have now made a unidirectional device, a true unidirectional device. In order to resolve that, we will put another rectifying diode in, again at 1 picofarad, and you can see that that would approximate a 2 picofarad total capacitance, significantly lower than the TVS on its own. For a bidirectional device, we could use a similar structure here that again would give you an approximate 2 picofarad capacitance. If you want to get really clever about it, you could build a bridge rectifier with a TVS in the middle, and then the TVS will offer about 1 picofarad total capacitance, and you would never experience a VF on the TVS. The steering diodes would prevent that. The devices can be packaged up in a number of ways, from simple single devices through dual devices useful for differential signaling such as CAN bus, and then, for example, this quad device aimed at high-speed USB 3 data pairs. This slide shows details of the naming convention that we use for many of our protection products, and so you might want to pause on this slide if you need to decipher something. A number of these parts are design registerable for distribution, in particular anything automotive signified by the Q on the end of the part number. To summarise then what we've discussed about TVS is that these are devices intended only for transient events and they're not a steady-state device. VRWM is a working voltage, and you can put a 3.3 volt TVS onto a 3.3 volt voltage rail. These protect against under or over voltage events only. The bidirectional devices add a negative working area, and that power ratings are measured in a very short-term manner, and they are not repetitive as the die heats up. And that high-speed data connections, you need to consider the capacitance of your TVS device. And now we'll move on to talk about some of the circuit configurations we might use to protect against some other events. We'll begin with reverse polarity protection. Wherever a usable replacer battery is provided in an automotive or portable device context, you can be fairly sure that some idiot's going to wire it up the wrong way around. The simplest way to protect ourselves against this eventuality would be simply to put a reverse blocking diode into our power rail. If we were to use a regular silicon diode, then we would experience a relatively high VF, but we'd have a good rugged device with a high junction capability. If we used a Schottky device, then we'll get a lower VF, but it's a rather less rugged device than the silicon diode. The Diode Zinc SBR technology combines the low VF of a Schottky type device, but with the ruggedness of a silicon diode. If we were to consider a 5 amp rail for this, then you can see that our power losses would be as high as 4.5 watts for a standard silicon diode and down as low as 2.5 watts for an SBR device. Obviously this is a very simple solution. It's very easy to implement and it should be relatively cheap to implement. Let's move on to the idea of using a MOSFET switch on the high side instead. If we were to do this using a P-channel device, then this is really easy to do the gate drive for. Just simply tie the gate drive down to the negative rail. Then, if the input voltage is the correct forward polarity, the device is switched on strongly, and we simply have an RDS on loss through the device. If the input polarity is incorrect, then the device will not switch on, and no current will flow. The RDS on losses in this case will be significantly lower than the losses through the VF of a diode. However, we're generally fairly aware that the performance of P-channel MOSFETs is not as good as the performance of an N-channel MOSFET. In the P-channel case, we might want to consider that the VGS must be limited within the maximums that the device can tolerate. If the input rail is higher than that, say a 24 volt rail, then a simple limiter like shown can be implemented to keep the device safe. If we wanted to use an N-channel device to get that lower RDS on, we need to do something about the gate drive. We need a positive VGS. The source is on the input now, and that means we need a higher gate voltage than the input to our circuit. So we need some kind of charge pump device or similar. Always bear in mind the body diode of the MOSFET. If you put the MOSFET the wrong way around, this simply isn't then going to protect you against reverse polarity, because the body diode will conduct instead of the channel of the device. If we were to use a 40 milliohm MOSFET with that same 5 amp rail as used on our previous slide, our power dissipation is now down as low as 1 watt. Similarly, we can use a low side MOSFET. If we use an N channel on the low side, then you have the same simplicity benefits that the high side P channel had with the lower RDS on of the N channel, which seems like a win-win situation. However, there are certain circumstances where you cannot break ground continuity, or you don't wish to. For example, in automotive, you want to use chassis ground and keep that continuous. This type of circuit can be useful in handheld and mobile devices. Let's have a look at a simple over voltage protection scheme. Again, we'll use a high side MOSFET and a P channel. We'll tie that gate down to ground again to switch the device on, and now we need some kind of simple circuit that will monitor the input and switch this device off when the input voltage goes above a given threshold. That circuit can be as simple as this. When the input voltage goes above the Zener voltage, the bipolar transistor begins to conduct, pulling the MOSFET gate high and thus switching it off. Note that as compared to our reverse polarity protection scheme, the MOSFET is now placed the other way round, again because of the body diode. So we start to consider overcurrent protection. The simplest device that we can use to do overcurrent protection is a fuse. Sadly, they're very slow, with a 3 amp fuse taking more than a second to blow at 10 amp current. They're not resettable, they require user intervention to replace them. They have their uses in preventing fires, for example in a mains lead in the UK, where each mains lead has a fuse and that's there to protect that lead alone. But in terms of an electronic circuit, they're not generally considered that useful. There are resettable positive temperature coefficient fuses, which again are somewhat slow to trip, and when they are tripped, they've not actually isolated the circuit. They have a hold current that, although lower than the trip current, still means that power will continue to be dissipated in the circuit that's supposed to be being protected. They can reset if they're allowed to cool, but after they've tripped for the first time, they will suffer a permanent increase in their resistance and thus lowering their trip point for the future. So a useful tool for doing an overcurrent protection scheme in a circuit is the current monitor. Obviously, if we need to trip at a certain current, we need to measure that current. A current monitor device like the ZXCT1009 is a transconductance amplifier. It will output a current that is proportional to the voltage measured across the sense resistor, and then the output resistor will translate that current back to a voltage level. This can then be used to trigger a disable mechanism, which would advise to probably latch. Overcurrent situations are often caused by an external fault that will require user intervention to clear. So if we put all of those elements together into this circuit, you can see that we have combined the transient voltage protection on the front end with the TVS device, reverse polarity protection with the first P-channel MOSFET, again with its gate limiter, followed by an overvoltage protection scheme with another P-channel MOSFET placed in the other direction, and then we have a current monitor measuring the input current to our circuit downstream, and that would trip a latching circuit, again using the same MOSFET as the overvoltage protection scheme to disable that voltage rail input if necessary. The thing about this kind of circuit is that it's entirely autonomous. You're not reliant upon a monitoring microprocessor to do anything here. If the processor has crashed or is busy elsewhere, this circuit will just look after itself. Again, a number of the parts that we've discussed would be design registerable. For example, any of the automotive MOSFETs or current monitor devices. So we've discussed some of the circuit design ideas and schematics that you might use in a protection scheme. Let's have a think about some of the layout considerations. A concept that I've heard a number of times through my career is that layout really isn't that important. I would say layout isn't important, it's critical. Poor layouts cost more money. They might need extra layers for routing, they might need 2 or 3 goes to get the job done, and if you have a poor layout around a microprocessor, an FPGA, causing EMC problems or some sort of production yield issue, additional countermeasures placed around the outside will again cost more money. Good layouts make the best use of the components that you've paid for. For example, if you've paid extra to buy a 10 milliohm MOSFET instead of a 15 milliohm MOSFET, why would you do that if you're then going to put an additional 5 milliohms of trace impedance in the way? Let's consider an overall PCB design. A good approach is to maintain a perimeter. By that I mean place any high-speed signals, high-speed circuits and sensitive items as close to the middle of the PCB as you can. Keep them away from the edges. We discussed the concept of protection margins previously, and now let's have a protection perimeter. And in this area we could put low speed, DC power supplies, this kind of thing. It doesn't have to be empty, but keep the high speed and sensitive stuff away from it. Place any connectors in this outside area. And in placing the protection devices that go with these connectors, such as TVS or capacitance, then you can keep external threats and spikes are intercepted before they get to your sensitive area, and any noise generated by your circuit will not make it out onto any external leads. Within that region, it's also a good idea to keep all your ground planes tied strongly together, and this should also provide some defense against handling damage from ESD during production. If we consider the humble decoupling capacitor, it's very important to minimize path inductances. Something that's quite commonly seen would be to have a length of PCB trace over to a nearby ground via as the ground connection for that decoupling cap. If we redraw this in schematic terms, you would have an inductance of approximately 1 nanohenry per millimeter of the trace, and the via in a standard FR4 PCB would be in the order of 1.2 nanohenries. If that trace is 5 millimeters long, then we've got a total of 6.2 nanohenries of inductance in series with a decoupling capacitor, exactly where we don't want inductance. In order to reduce this, obviously the simplest thing to do is simply to move the via closer to the pad. Get rid of that 5 millimeters of trace, and we've got rid of 5 nanohenries of inductance. In order to reduce the inductance of the vias, let's use 2 of them, putting them in parallel, and now we've reduced the total inductance to 0.6 nanohenries, down from the 6 that we had before when we had a trace and single via. Tie these solidly with a solid copper area for the lowest possible impedance. As we discussed on the previous slide, it's important to place decoupling and protection devices adjacent to any connectors on the PCB. So for example, if we have a connector here, we'd place our TVS and capacitor as close as possible to it with simple, straight and as heavy as possible tracking. With the devices placed so, then any external noise or spikes coming in will simply pass through the capacitor or TVS as appropriate and straight back out and not even get to the sensitive parts of your board. To summarize everything that we've discussed then, Protection is a combination of design practice and component selection. It's important to understand what characteristics of the components mean and how to use them. You need to decide what you're protecting against, and you can't aim for perfection. You will never make a circuit that can be rugged against absolutely everything the world can throw at it. Pick the right parts, make sure the circuit does what you want, minimize impacts on your real circuit, the thing you're actually trying to do, and make sure it's laid out correctly. Maximize the benefits of those components that you have paid for. If you have any questions about this presentation, please send them through either your Diodes Incorporated distributor or representative.